Welcome to this video presentation where we'll be looking at the West Mock 2024 examination proposed solution for pure mathematics with mechanics paper 3. Now the question you are looking at is a question on application of calculus in mechanics, and the question reads: the position vector of a particle P of mass 6 kilograms at any time t is given by r is equals to cos t divided by 2I plus sine t divided by 2j meters. A. Show that the position and acceleration vectors of the particle are oppositely directed. Show that the velocity and acceleration are always at right angles to each other. Given that t is equals to pi, find c, the magnitude of the momentum of the particle. Roman 2. At time t equals to 0, the position vectors of two particles r and q are 5I plus 20j meters and negative 10I minus 5j meters respectively. The particles have constant velocities, negative 2I minus 5j meters per second and 3I plus 5j meters per second respectively. Find the position vector of q relative to r after 3 seconds. Now, this is the expression for the position vector of the particle P at any time t, and here is the mass of the particle. The first question is that we are required to show that the position and the acceleration vectors are oppositely directed. What does that mean? It means they are parallel but moving in opposite directions. So we are required to show that the acceleration is equals to negative lambda times the position, or the position is equals to negative lambda times the acceleration, where lambda is a positive constant. Now we just have to find the acceleration vector of that particle and then compare it with the position vector to see that one is a scalar multiple of the other, with the scalar being negative. All right, let us proceed. We know that the acceleration is equals to the derivative of the velocity, where the velocity is equals to the derivative of the position vector. So I will need to find the derivative of this position vector to obtain the velocity, and then the derivative of the velocity to obtain the acceleration. Now let me start with the velocity. So I will find the derivative of this expression to obtain the velocity, and differentiating cos t divided by 2. When I differentiate cos, I have negative sine, and when I differentiate this angle t divided by 2, I have half. So the derivative of cos t divided by 2 is negative half sine t divided by 2 of cos I. Then plus the derivative of sine is cos, and that of this angle will be half. So the derivative of positive sine t over 2 will be positive half cos t over 2 of cos j, velocity in meters per second. But I have to go one step ahead and find the acceleration. Therefore, I'll need to take this expression of the velocity and differentiate it again. So A is equal to dv by dt, which is equal to differentiating this, sine gives cos, then differentiating this angle t over 2 is half. Half multiplies with negative half and gives negative 1/4 cos t divided by 2I. And doing the same thing here, I differentiate t over 2 is half. Differentiating cos is negative sine. So what is half times negative half? Negative 1/4 sine t divided by 2j meters per second squared. Of course, is acceleration. So we have the acceleration vector to be this. Now notice that negative 1/4 is common to these two terms. So I can factor out negative 1/4, and I have A is equal to negative 1/4 into cos t over 2I plus sine t over 2j meters per second squared. Now, if you compare this expression inside the bracket with the position vector, you will see that they are identical. So I can say A is equals to negative 1/4 r, where lambda is equals to 1/4. So I have shown that the acceleration vector is equal to negative 1/4 multiplied by the position vector, and lambda of course is 1/4, which is positive. This makes the whole scalar negative. Hence, A and R are oppositely directed. Now, the B part is we are required to show that the velocity and the acceleration vectors are always at right angle. We need to show that their dot product equals 0. As easy as that. Two vectors are perpendicular when the dot product of those vectors gives you 0. So I will take the expression of the velocity and find the scalar product with that of the acceleration and then show that the result is 0. So this is the expression of the velocity which I obtained from the first part. Here is it. Negative half sine t over 2I plus half cos t over 2j dot the acceleration vector. Here is it. Negative 1 quarter cos t over 2I minus 1 quarter sine t over 2j. Now, to find the dot product of two vectors, I will essentially multiply their corresponding coefficients. So I will take the coefficient of I, multiply it with the coefficient of I in the other vector, and I add it to the product of the coefficients of j of those vectors. So negative half sine t over 2 times negative 1 quarter cos t over 2 gives me positive 1/8 sine t over 2 cos t over 2. That is it. So I add it with the product of the coefficients of the j component. So half cos t over 2 times negative 1 quarter sine t over 2 gives me negative 1/8 sine t over 2 cos t over 2. Now, the product of positive and negative gives me negative, and these two terms are identical. So they subtract each other and gives 0. So I have indeed shown that they are always at right angle as their dot product gives me 0. So hence, V and A are always at right angle. Now, the next part of the question is that we have been given that the time at that instant is pi. Let's find the magnitude of the momentum. So the magnitude of the momentum is given by the mass multiplied by the magnitude of the velocity. And the velocity vector was given by this, and t is equal to pi, so I will substitute pi everywhere else I see t. So I will be looking for negative half sine pi divided by 2I plus half cos pi divided by 2j meters per second. And of course, when I evaluate all of this, pi is 180 divided by 2 is 90, and sine 90 gives me 1. And 1 times negative half, of course, is negative half I. Cos 90 is 0, so this term vanishes. And the velocity vector, and the velocity when t is equal to pi is negative half I. But let's find the magnitude of that velocity. So I just do away with the sign, and I do away with the unit vector, and it gives me half. Or better still, you can take negative half, square it, and find the square root, which of course will still give you half. So anyway, you are going to have the answer half. Now, I just need now to then multiply it by the mass. So the magnitude of that momentum will be the mass 6 times half, which is 3 kilogram meters per second. So the magnitude of the momentum of that particle at time pi is 3 kilograms meters per second. So we are through with the first part of the question. We can now move on to Roman 2. We were told that when t is equal to 0, then the position vector of a particle r is 5I plus 20j meters, and its constant velocity vr is negative 2I minus 5j meters per second. And the position vector of the other particle, which is q, is negative 10I minus 5j meters, and its constant velocity is 3I plus 5j meters per second. We need to know that the position vector at any time t is given by r is equals to the initial position plus t, which is the time, multiplied by the constant velocity. So I'm going to use this principle or this knowledge and then write out the position vector of particle r and q. So the position vectors of particle r and q are given by particle r will be 5I plus 20j, then plus t multiplied by its constant velocity. And for particle q, I will have negative 10I minus 5j plus t multiplied by its constant velocity, which is 3I plus 5j. Now, I've been asked to find the relative velocity of q, that is the position of q relative to r. is given by, this is a notation, and it's equals to the position vector of Q minus the position vector of R. So this is the position vector of Q, then minus the position vector of R. So I subtract. So I'm just going to open the brackets by multiplying negative to each term. So I'll be having negative 10i minus 5j plus 3ti plus 5tj minus 5i minus 20j plus 2ti plus 5tg. I have just distributed t into the bracket before bringing the terms together. Now I can bring like terms together, terms in I together. This is a term in I, a term in I, a term in I, and a term in I. So negative 10i minus 5i gives me negative 15i, and positive 3ti plus 2ti gives me plus 5ti. Let me move on to the terms in j. Negative 5j minus 20j gives me negative 25j, and positive 5tj plus 5tj gives me 10tj. Now let me now substitute t as 3 because I was asked to find the relative positions when t is equal to 3 seconds. So if I plug in t as 3 seconds, I'll be having 5 into 3i, then 10 into 3j. Then multiplying out the bracket and subtracting, I will see that the first term vanishes because negative 15i plus 15i gives me 0, and I'm left just with negative 25j plus 30j. That gives me positive 5j. So the position vector of Q relative to R after 3 seconds is 5j. We have come to the end of this presentation, but if you do have questions or doubts or corrections or whatnot, please do leave it in the comment section below. I'm Tata NS, and do have a wonderful day.